Suppose we are interested in finding an estimator theta hat of theta based on samples x1, x2, xn. Now, this is a very common problem in statistics, and there are lots of methods to deal with this sort of problem. But suppose that the estimation procedure is too complex to solve. In such situations, we take recourse of what is called the resampling procedures. More generally, in this session, we would be talking about the bootstrap procedure. In the last session, we had learnt about the jackknife procedure, and in this session, we would extend the idea of jackknife procedure and learn what is the idea behind the bootstrap procedure. And finally, we shall be using bootstrap techniques to see how to find or how to estimate or how to perform a variance estimation of a statistic. We would see some examples and the algorithm to use, and further we shall be using the bootstrap technique to find the estimation or to find the estimation of a sampling distribution. Introduction to bootstrap. Consider x1, x2, xn follows IIDF, and we are interested in the problem of finding an estimator theta hat of theta. We are typically interested to find an estimate of variance of theta hat also for inference purpose. Now, the quality of the estimate depends on the accuracy of the model and or the validity of the asymptotics of theta hat, but sometimes it is really difficult because the estimation problem is too complex, and here we cannot take the ordinary approach. So, we have to take recourse of resampling technique like the jackknife and the bootstrap. In the previous session, we had done jackknife. Just to recap what jackknife is. So, a jackknife estimator T n minus 1 I is T n minus 1. So, an estimator based on x1 to xi minus 1, xi plus 1 to xn, that is on x1, x2, xn excluding xi, and then I can find T jack, which is Tn, that is the true estimator or the estimator based on n, minus B jack, where B jack is the bias of jack, which or the jackknife estimator, which is nothing but n minus 1 Tn hat minus Tn, where Tn hat is 1 by n summation I runs from 1 to n Tn minus 1 comma I. So, that means we are performing n estimators here, or we are obtaining n estimators here each time based on n minus 1 samples, deleting the ith value. So, I runs from 1 to n and taking a mean of it, we are getting Tn hat. Now, it can be shown that the jackknife estimator is a reduced biased estimator of theta. Now, we take this idea and have an understanding about the bootstrap principle. So, what is the bootstrap principle? The basic idea behind bootstrap principle is that a data set of size n can have 2 to the power n minus 1 non-empty subsets. Note that the jackknife only uses n of these subsets. Now, we can ideally improve the jackknife by taking more and more subsets from this 2 to the power n minus 1 non-empty subsets. Now, this was not practically feasible before the advent of computers. Only when the statistical computing became stronger, the idea of bootstrap came into place. So, the bootstrap was introduced by Efron 1975, where it borrows non-empties, the 2n from those 2n minus 1 non-empty subset, it takes many of them and tries to perform the inference. As an example, let's see about the bootstrap method of variance estimation of a statistic. So the problem is usual. We have a random sample from x1, x2, xn which follows IID, a distribution f, and f can be parametric or not, or may not be parametric. And suppose we are interested in, say, theta, which is theta of f is the parameter, and theta hat, which is Tn x1 to xn, is our statistic or the estimator. Now, what is variance of Tn? Now, variance of Tn is integral of Tn minus integral of Tn d pi f of xi, that is the mean square, d pi f of xi. That is a simple variance formula. Now, we typically estimate this variance of Tn by replacing this f by an f hat in the variance form, and we say that that is an estimate of the variance of the estimate. So, that means if we do that here, so we replace f by f hat, so we get the form to be variance integral of Tn minus Tn d f hat xi square d pi f hat xi, and so that is nothing but variance of Tn x1 star, x2 star, xn star given x1, x2, xn, where x1 star, xn star follows IID f hat. Now, we define the bootstrap estimator V boot is equal to variance hat of f Tn. Now, suppose f hat x is the empirical CDF. So, one of the estimates of f hat can be the empirical CDF. So, what is an empirical CDF? It is 1 by n summation I runs from 1 to n, indicator of whether xi is less than equal to x or not. That is f hat x. So, then if theta is equal to, say, let us take theta, which is, say, expectation under f x1, which is xn bar. So, theta hat is xn bar. Then variance of xn bar comes out to be 1 by n variance of xi, which is approximate equal to 1 by n integral of x minus integral of x d f hat square d f hat x, and that when computed comes out to be the traditional variance estimator of x bar. So, the bootstrap variance estimator is thus equal to the traditional variance estimator if we consider f hat to be the empirical CDF. Now, consider another case where x1, x2, xn follows IID normal mu sigma square hat with mu and sigma square both unknown, and suppose we are interested in, say, mu. Then obviously theta hat is the mean based on those x samples. So, we are writing here at x bar n, and variance of x bar n is sigma square by n, and under the estimate of which comes out to be sigma hat square by n, and that is the traditional one. Now, to obtain a bootstrap estimator, note that the estimate of f is of the form normal mu hat sigma hat square. So, integral of x d f hat is expectation of x given x follows normal mu hat sigma hat square, which is mu hat. Again, variance of the bootstrap comes out to be 1 by n integral x minus mu hat square d f hat, which is sigma hat square by n. So, which is nothing but variance of x1 by n. So, here also we are getting more or less rather the same form. Variance of boot is equal to the traditional form. Now, consider a more complicated form where we are interested in a, say, constraint maximum likelihood. So, for example, we are interested in the equation log of probability y I equal to 1 given xi by 1 minus probability y I equal to 1 given xi equal to alpha plus theta xi. Note that this is nothing but a logistic equation with covariate xi and yi taking the value 1 and 0. Now, we observe the paired observation yi xi, I runs from 1 to n and yi assumes 0 1. Now, suppose a further restriction is imposed and which says that probability of y given x is convex in x. Now, in this case, we can obtain a numerical value of Tn for a given data set by solving a set of constraint likelihood equations, but we cannot get any explicit expression for Tn in terms of x1, x2, xn, and hence we cannot evaluate the integral for the variance functional form that's given in equation star. And so, the traditional approach of variance estimation fails here, and that is, in this situation we can really see the effectiveness of the bootstrap. So, we are now interested in the use of bootstrap variance estimator when explicit evaluation of the integral is not possible, and the explicit evaluation may not be possible because an explicit expression may not be obtained, or the explicit or the integral is mathematically extremely complex. So, what do we do? Suppose we have the given sample x1 to xn. We use this to compute f hat by drawing b independent samples, say x1 b star, x2 b star, xn b star, where b runs from 1 to b from f hat, and then compute Tn b star, which is Tn x1 b star, x2 b star, xn b star for each. Then what do? We can find the variance of the bootstrap sample. So, V boot b, which is nothing but 1 by b summation b runs from 1 to b, because we have taken capital B samples, and then the normal summation, the normal variance formula. So, as if Tn b star is an observation, and we are getting b such observations, and we find the variance of those b observations. So, V bootstrap b is the bootstrap estimator of Tn, and it can be seen that from the law of large numbers, limit b tends to infinity, V boot based on b samples tends to V boot. Now, we extend this idea of bootstrapping for estimation of sampling distribution of Tn. Now, it is not obvious how to estimate the entire sampling distribution of Tn by jackknife, because jackknife is based on n out of those 2n minus 1 non-empty subsets. But the bootstrap can be readily used to estimate the entire sampling distribution. So, more generally, consider the problem of estimating the sample distribution of any random variable, say Rn, x1, x2, xn, comma f, and then hfx says that is the empirical CDA, has an empirical CDA for, like, say, probability Rn x1 x to xn comma f is less than equal to x for some x which belongs to the real line R, where x1 to xn as IIDF. Now, in the traditional approach, the idea is to obtain a simple parametric form of HF and then substitute f hat. And in the bootstrap approach, what happens is the bootstrap samples are obtained, and from that the empirical CDF is calculated. So, that means H boot x is H f at x probability of Rn x1 star, x2 star up to xn star comma f at is less than equal to x, where x1 star to xn star is IID f at. If H boot x cannot be calculated, then we can use H boot bx. So, that is based on b subsamples, which is 1 by b summation b runs from 1 to b I, that is the indicator of Rn x1 b star to xn b star comma f at less than equal to x, where x1 b star to xn b star b equal to 1 to b are independent bootstrap samples. So, even if we do not need to assume a functional form of HF. Rather, based on the bootstrap samples, we can compute H boot, and from there we can find the sampling distribution of Tn, or we can estimate the sampling distribution of. In today's session, we have learned about a bootstrap principle, how we can use bootstrap principle in complex estimation procedures to get an estimate of the variance of the statistic and to get the distribution, sampling distribution of the statistic. In the next session, we would be seeing a few more applications of bootstrap in context to different problems.